So you've won that commercial solar project. Now there's the question of what kind of on-site documentation are you going to provide to your installers? Hi, I'm Veli from Greenwood Solutions. This week we're looking at commercial on-site documentation. So after watching the presentation, you'll understand what kind of documentation to put together, how to present it, and who's actually going to use it. Now, if you like what you see and you want us to make more of these videos, hit that subscription button. Let's get stuck into it. The sheer amount of documentation that surrounds a commercial solar project is immense. In addition to the standard electrical paperwork required, there's also specific project management and site documentation, and of course all the customer paperwork. This presentation will attempt to systematically look at what is required from a site documentation perspective. The team has been assembled. They're ready to start the first process of getting the feet onto the roof. The solar component is over 200 kilowatts. The roof is vast, actually a cold storage facility, and as part of the team jump into the EWP and start ascending, questions are asked. Where are we depositing these feet initially? Where are they finally going? Where is the A3 laminated site folder showing the actual feet layout? Now this does happen. Creating and having available when needed the right documentation is important for so many reasons. At the beginning of any site works, the project manager, site supervisor, must organise a folder containing all the relevant information concerning the construction, the procedure, and the processes involved in putting the system together physically. Step 1. Determine where the feet, fixings, etc. will be deposited. Remember, double handling is inefficient and should be minimised at all costs. Now, what about that feet layout drawing? The designer must provide on-site documentation showing the actual position of the feet, the number of rows, the variations between rows if applicable, and any other pertinent information. Now, if well organised, the assembled feet are brought to the roof and directly dropped in their approximate positions ready to be fixed down. In this particular project, we are installing rail FTR, flat to the roof. Now, all aluminium rail has a coefficient of expansion, and the manufacturer of the particular rail being used will advise what is the maximum unbroken length of rail, joined segments of course, that is allowed. For example, the Clenergy PV Easy Rack total rail length is recommended not to be over 30 metres, considering rail's thermal expansion problem, and there's a link below. In this example, due to roof configuration and other design limitations, the unbroken rows will accommodate 20 panels, and this has resulted in the following design. 20 panels per row, total of 32 rows. Each row length is 20,660 millimetres. Individual rail sections at 4,200 mil. Step 2, put together a rail cutting schedule. This is a sort of schedule that can be handed to personnel responsible for preparing the rail. So you can see the row number, the new lengths used, cut this, waist left, and top rail length, new length used, etc, etc. In this case, it is fairly easy to follow as all rows are equal and the waist left from the top rail is not used with the bottom rail. Pretty lucky, eh? We now have all the rail cut. We know the total rail length, how many panels per row, and the feet spacing. Are we missing anything? Yep, the rail cantilever. What we are talking about here is the amount of rail that hangs over the first and last foot in the row. Thankfully, as part of the rail design, etc., this has been calculated as being 300 millimetres, but has this been communicated to the install crew? In other words, is there a drawing? And there is. And you can see in this drawing it shows the space between the feet, the total rail length, and the overhang of 300 mm. Got to splice rails and attach to feet, but before, hang on, we have to attach the feet to the roof, and in this case we are not penetrating the roof sheet but clamping onto a rib. Okay, we clamp onto the rib. That sounds easy. We use a wrench or drill and go for it. No, we don't. Step 3. Clamp roof fixing torque schedule. In our case, we're using a clamp that has 3 sections that require 2 by different torque settings. Bottom section 16 to 20 Newton meters, middle section 16 to 20 Newton meters and 10 to 12 Newton meters, and the top section again 16 to 20 Newton meters. Hang on, do we even have a torque wrench? The torque settings have come straight from the manufacturer, and if not followed, fill in the missing gaps. Okay, so now we can start with fixing the rail. So the rail has to be spliced together and then connected to the roof fixing system used. The install crew now has access to the site documentation showing rail feet interface, cantilever measurements and torque settings. Depending on your modus operandi, the next step is laying the cable tray. So what cable tray is being used? How long are the runs? How do we transition from one size cable tray to another? Where's the cable tray schedule? Step 4, cable tray site plan. And as you can see here, we have a configuration of panels with different size trays being used. So you can see we're using 150mm cable tray and 300mm cable tray. In this table, we are showing the cable tray run number, the tray size, the tray length, and contains which inverter, maximum power point tracker and string. In this case, we are using an inverter that has 6 maximum power point trackers with 2 inputs each. We have a cable tray plan, and the tray has been laid down, affixed to the roof, transitions have been worked out, and all is good in the world. The guys have been working hard. There have been no hold-ups so far, so the next step is getting the cable to the roof and slapping it down. You guessed it, another step, the cable schedule. In this example, we are using 4mm squared solar twin DC cable, but in some bigger jobs where the DC runs are longer, 6mm cable is used. Without a DC cable schedule, confusion may occur and 6mm squared may go where 4mm squared should go and vice versa. And what about the strings? Are we paralleling strings or not? And hopefully all the DC volt drop calculations have been made as well. So in this table you can see the cable type and size, which inverter it's been connected to, the average length of run in meters, the termination point, the DC volt drop percentage, and the voltage at maximum power point. And we're assuming the panels have a short circuit current of 10 amps, no parallel strings. Now the inverters. Now we need to put together the inverter schedule. In this case we are using 3 inverters. 2 of 3 are 100 kilowatt capacity and the third is a 50 kilowatt inverter. They are all installed at a roof inverter station in conjunction with the grid safe secondary protection board. The maximum distance between the inverters and the secondary protection board is 7 metres. Connection is to the MSB, which is 30 metres away in the plant room. Step 6, the inverter schedule. So in this table we show the inverter number, the brand and model, the location, the distance to the secondary protection board, the cable type and cross-sectional area, and the volt rise in that particular run. Conclusion. Large commercial solar projects contain a myriad of tasks that need to be organised, implemented and completed. The task of on-site documentation is not to make things laborious, but to help streamline all the processes on site. If you have a plan, it can be executed, and developing on-site documentation helps with this. Thanks so much for watching our presentation on solar on-site documentation. I'm Veli from Greenwood Solutions. Now if you have any questions, any inquiries, any answers, feel free to get in contact with us. If you like what you see, hit that subscription button. See you next time in part 2. That's right, there is a part 2.